I think I upset it. There it goes. Elimination, addition, and radical. Okay, so we've got those nailed down. Remember, the radical splits into substitution and eliminate, or substitution and addition type systems. Okay? So once we know our 5 basic types, we need a couple different ways to address those. Number one would be definitions. And because we rarely look at a question and it's just what is the definition, we're looking at reactions, we want to be able to look at structures. We want to see some structural images that represent each of these things. So let's start with acid-base. How did you know you have an acid-base reaction? Okay, there's an acid and a base. Okay, that's a nice, easy first jump in there to an acid-base reaction, but you're now defining our reaction with the terms themselves. That doesn't work out so well. So far as I think we're jumping in with something else here.
Transfer of a proton.
Transfer of a proton. Okay, that's the only thing that happens. Okay, so there are reactions that will transfer, and I actually have a typo there. I'll address that in a second. That transfer protons and do something else. Okay? That's not an acid-base reaction because there's an and something else. Acid-base is solely the transfer of a proton. Okay? We aren't doing nuclear chemistry. This is not a proton embedding into the nucleus of another atom. Okay? This is a proton being attracted to the nucleus of another atom and being chilling on the outside. Because it's now chilling on the outside and it's not part of the other atom, it's a distinct species, we give that a name. That name would be hydrogen. Okay? First element on our periodic table, composed of simply a proton. Okay? So what is the typo that I have up here? Transfer of a hydrogen only. Well, isn't it hydrogen?
But without the electron.
There's our defining factor. When we're talking about the transfer of a hydrogen only, remember Farzan said transfer of a proton. Okay? Well, hydrogen is a proton if that's all it is. There's no electrons associated with it. Can we transfer a hydrogen with electrons? Yes. That would be known as a hydride. That's not acid-base. Acid-base is a positive hydrogen, also known as a proton or a hydrogen cation only. The instant it becomes negative and it's coming with electrons, we're not doing acid-base. Technically, we're doing something else, so we have to be careful with that terminology. Okay? Can a hydride react with a hydrogen cation? Yes, then it's an acid-base. Okay? So we have to be careful where all our lines fall. Okay. What about substitution? Can we put words to substitution? Yes, you can. So SN1, SN2, those are good kind of word associations, but the issue with SN1 and SN2 is not so much the substitution, but those are mechanisms of how the substitution reaction happened. To be able to look at the mechanism, I have to first recognize that it's substitution. So how do I recognize it's substitution? Okay, substrate and nucleophile, that's better. Leaving group, so we're naming the components of it. What we're looking at is the exchange or a transfer of an atom other than hydrogen. So when you were talking about leaving groups and your nucleophiles, what's happening? The nucleophile exchanges for the leaving group. May have said that English-wise backwards, but you get the idea. Okay? What about an elimination?
Elimination of sigma bonds.
Okay? A loss of sigma bonds. I lost sigma bonds in a substitution. I lost sigma bonds in an acid-base.
And creating pi bond.
Okay? And also the formation of a pi bond. So we have the loss of sigma bonds, but in the process of that loss, we result in the formation of a pi bond. Most typically, we associate elimination reactions with alkenes. Okay? That would be a double bond. Notice this says pi bond, not double bond. Why? Could we form something other than an alkene? Yes. Could we form something other than a double bond? Yes. These are supposed to provide the most broad and general definitions as possible. Addition, give you a couple cheats on that one. First one, it's the opposite of an elimination. Okay? So that's the easiest. The more in-depth answer would be the loss of a pi bond, resulting in the formation of 2 new sigma bonds. Okay? And then our radical ones, you can tell how much I like them, do just weird stuff. Okay? So that's our single electrons. We've got very limited circumstances under which radicals are necessary, but they are important to use, and when they appear and when we need to be aware of them, we have to drop those in. After that, we need reactions. We need to know what these look like. Okay? Are there any words up there that you're like, I need a little help with? When I was putting you on the spot. You see anything up there you're like, can you define that for me? Make sure I know what it means. Yeah, so everybody's good? So guess what the next question is going to be? I see a pen at that board. I see a pen at that board. I see a pen at that board. I see a bunch of pens up here. Draw examples. And remember, we have X amount of content. The longer it takes you guys to get through drawing the examples, the less time you get to spend on harder content. Whenever I show a reaction, I almost always try and show the simplified version of it, because the rest of it is cluttered there to confuse you. So ignore everything else. I don't care that there's a CH3 out here on Sam's substitution reaction, because it didn't do anything. The chemistry happened here. Why do I know the chemistry happened there? That's where the bromine is. Why would the bromine leave? Because, sorry, I didn't hear that. No, I won't say I didn't hear it. What'd you guys say? Why did iodine not come in over here? Why is there charge there? But according to Sam, the bromine did not leave until the iodine came in. So I don't accept the bromine leaving, generating a charge.
Bromine is more
Electronegativity. We're finding the electronegative elements, like our halogens. Those are starting to withdraw electrons, generating partial charges, which is what's going to force the chemistry. It all comes back to electronegativity. How does that distribute the charge and allow our different reactions to happen? So when we look at a structure, find those electronegative elements, focus your attention there. And if you're going to try and do a reaction, which bond are you going to break around that electronegative element? If you're lucky, there's only one bond. That was first semester. Second semester, we'll start with 2 bonds. Towards the tail end, we'll have 3 or 4 bonds. Okay? And to make matters worse, not only will we have 3 or 4 bonds, and you'll have to go through and decide which of those is most or least positive, okay? You'll have to then test it and be like, I'm going to take the most positive, the most negative, and react them and see what happens. Oh, that didn't produce anything useful. Okay, what do? You take the second most positive, the second most negative, you react them. Oh, that went somewhere. So you will have to come up with a predictive ability of looking at these structures. That predictive ability comes with drawing lots and lots of structures, and ultimately drawing lots of dead ends. I took these 2, mashed them together, and it didn't work. Don't erase it. Put a line through it. Whoops. Try again. Okay, you get credit for that. Okay. So in our substitution and elimination, to kind of speed our process along a little bit here, characteristics. You'll notice that when we talk about substitution and elimination, usually in anybody's first semester class, they don't give you that spider diagram. Everybody familiar with a spider diagram? You have a central molecule, and then you have 20 reagents that spider out away from it in a big kind of circle. Sometimes they show it, sometimes they don't. My students know it because they had. No? Okay, you'll see one in a little bit. Substitution and elimination don't get those. And that's because there's so many different substitutions and eliminations that we could possibly run. So we aren't going to try and list the hundreds of leaving groups with the probably thousands of nucleophiles. That would be stupidly overwhelming. So what we do instead is simplify this down. So our substitution reaction, that's the one that's happening on top. How do we know that top one is substitution? Or rather, the bottom one is not? Pi bond. Look for those big clues. The bottom one has a pi bond. That can't be substitution. Simple. Okay? So that means the top one's substitution because it says substitution and elimination. LG for leaving group. NUC, nucleophile. SOLVENT, our solvent. Okay? Why are those things colored differently than the rest of the structures? Those things contribute to the reaction. And depending on the characteristics of those things, we get different substitution results. We get different elimination results. Those two were the majority of first semester OChem. Okay? So what you should go back and do, if you don't remember those, is review those basic pieces. Recognize what a leaving group is. What are characteristics behind that? What are characteristics behind a nucleophile? What are the characteristics of a solvent? How does that change how the reaction works? You might go, that's a lot. Yeah, that was most of first semester. I know, that is a lot. I did post, let's see, did I put it up there? I put my shorthand, kind of like Cliff's Notes, PowerPoint, for substitution and elimination on Canvas. So if you go into the lecture slides, so you go to lecture slides, there's another folder that I think I said review. That's the first thing in that. So those of you that had me before, all I did was cut out a bunch of slides, and it's something like probably 30 slides that real quickly just summarize, this is what you're looking for a nucleophile. This is what a leaving group is. Okay? Trying to draw your attention to those. Really, the only way you're going to remember that is practice. So that's where you got to keep going back, doing review. Alkene additions. What are our characteristics of alkenes for our addition reactions? Well, number one, I give you a big hint at the beginning of it. Probably an alkene. We need a pi bond. Typically with our addition reactions that we've talked about, they're non-polar pi bonds. So that's our alkenes and our alkynes. This is where we encounter our spider diagram. We've got one central molecule, and this is, I already saw it. People are like, yes. Okay. This is part of it. This summarizes one of our chapters from first semester. Okay. And bits and pieces of a couple of the other ones. You're responsible for all of these. Okay. Do you have them all memorized? No. Do I? Yes. Yes. I think I got them all memorized. Okay. But that comes with 15 years of you asking me questions and me being like, I don't know, I'm going to look at the book. Okay? It takes time and practice. That practice is first going to start with recognizing the changes, which we talked about with the synthesis activity. If I start at this alkene and I move to the lower right, I believe that is my right, that one. What are the changes? What changed in that reaction? I lost a pi bond, which means addition. Ooh, I have a word. With that word, we can go to the index of our textbook. We can look up addition reactions. Yes, that sucks. That's tedious. But it's going to get so frustrating, you'll want to stop doing it by memorizing it. It'll work. Okay? So it's an addition. What else changed?
2 sigma bonds were added.
2 sigma bonds were added. Well, that goes back to it being an addition, so give me more than that. I have an OH, which means in my reagents, what should I need to have show up in my reagents? An OH. Do I have an OH in my reagents? Yep. Buried inside H2O. What else changed? This is what happens when you do too many things at once. We have a chiral center pop up. Ooh, that was an awful chapter. We're like, ugh, chirality. Yeah. Okay, we got to worry about it. It comes back. It will bite you. Okay, but that's looking at the details behind the mechanism. I would argue we should take a step further back from that, and this is where I did too much at one time. Let's make that a little bit easier. What else changed? There's a bromine. What needs to show up in my reagents? Bromine. Is there a bromine? Yes. So by looking for those big changes, we can start to whittle down what's happening, and we can start to find that information in our textbook. A lot of second semester is going to involve looking things up. Okay? So if tutors start telling you answers, if I start telling you answers, that's bad. Feel free to yell at the tutors. Feel free to yell at me. Okay? You need to deal with this fighting through it all. Okay? So that's not bad. We talked about 2 reactions, substitution, elimination. Except I said that was hundreds matching to thousands for each of those. I'm not really good at math, but I think that scales our reactions up a whole lot. But if we just pretend it's just substitution, elimination, let's keep that. So just 10 more. So we're at, what, 12? Yeah. So there's a few more. Okay. Yeah, a few more. And we even brought in an alkyne. And this is where the old textbooks I disagree with, because they now say alkynes do their crazy own chemistry. It's the exact same chemistry as the alkene. It's still a nonpolar pi bond. It just happens that there's 2 of them, which means they have the potential to react twice. They also have the potential to react once if we specify proper conditions. There's our reagents. So our exception things. It's not really an exception, it's a limitation on the chemistry. Those are really important to memorize. Lindlar's catalyst and hydrogen with an alkyne, triple bond, will get you what kind of double bond? A cis, meaning those R groups are same side of the pi bond. Sodium metal, not ion, and ammonia will get you a trans alkene, where our R groups are on opposite sides of the pi bond. Those 2 reagents are of pretty critical importance to memorize when it comes to alkynes and our reduction summaries. The rest of them, what changed? You added hydrogen. Well, the very first reagent, what did we add?
Hydrogen.
H2. Okay. Second reagent, that was a bit obnoxious because it should be written there. What should be written there? H2. Third one down, H2. Again, rainy nickel being irritating again. H2. Go to the right, H2. Bottom one's really weird because we don't see H2, and that's because we got a weird mechanism. But when we're looking at our reductions, what's happening? We're adding hydrogen. So guess what reagent we need? Hydrogen. Okay? So trying to simplify and find those patterns instead of just saying this reagent does this. Okay? Try and step back from it. Okay, which gets us to our synthesis activity, which is what we started with. So our addition reaction. When we're looking at our addition reaction, our basics, lost the pi bond, the addition of 2 new sigma bonds. Okay? The pi bond has electrons, which means those electrons are going to react with something that is positively charged. Okay? We can get really fancy with our terminology and say that something with a positive charge is probably a Lewis acid. Because what is the definition of a Lewis acid? An electron acceptor. And for something to accept electrons, what charge must it be? Positive. There it is. Okay? So if we address our charges, we can pick up how these reactions work. Okay? By taking those electrons away from the pi bond to react with the Lewis acid, what happened to the other carbon? Well, it's now lost electrons, making it positive. What does it need? Electrons. What were we going to find in solution? A Lewis base, an electron donor, to share electrons onto the other side of it. Okay? And we'd end up generating our product. Depending on the regiochemistry, what things are attached to our pi bond is going to change the characteristic of where the Lewis acid and Lewis base go. Why? Well, if I take a look at that starting alkene, and I drew a resonance structure of it, let's switch it up and just say you drew a resonance structure of it, and you gave me this as a resonance structure. Is that a resonance structure? Yes. What I'm saying is the pi electrons move to that carbon, and then I stop drawing the hydrogens, right? Okay. Would you say that was a valid resonance structure for credit for that question? Probably not. What's your other option?
Electrons on the other carbon.
The electrons to the other carbon. Well, still charged. Why is the purple one better than the red one?
Positive is on the second.
Our positive charge is on the secondary carbon. It's close to more electrons. It's unstable because it's positive. What makes it more stable is having more electrons around it. So if I can put a positive charge near more electrons, a secondary carbon, it's going to be more stable. That means when I look at how that pi bond reacts with the Lewis acid and Lewis base, I'm really evaluating that resonance structure and saying, I want that positive charge to go to a negative one. Well, a Lewis base is an electron donor. I want that negative one to go to a positive one. That's my Lewis acid. Okay? So by recognizing the electronic effects of where I would like to put charge preferentially can dictate what my products come out at the end. Okay? And that's a lot of what the addition reaction is. If you've heard something about Markovnikov and anti-Markovnikov, my students know that I hate that. Okay? Because that rule is not talking about electrons. It's saying that hydrogen appeared at one position. Not hydrogen cation, not hydrogen anion, hydrogen appeared. That's like saying when I went out to the beach and I happened to notice some holes where a big toe showed up on the left side of this footprint. Okay? And I checked for another footprint, and I found the big toe showed up on the left side of the footprint. And I found another footprint, and it showed up on the left side. So my rule is that the big toe print shows up on the left side of the foot, or the left side of the footprint. Until what happens? Someone says, expand your field of view, and says, look at the other footprint. And where's the big toe in the other footprint? On the right side. Well, that's okay, because I'm famous, and we'll say one case, the big toe shows up on the left side, and on the other case, it is anti to my rule. So really what you're saying is you have no clue what happened or why things happened. You're just making a simple observation and just saying whatever didn't happen is now categorized as the thing that didn't happen. Yes, that is exactly what Markovnikov's rule is. Okay? For a perfectly legitimate and valid reason. He discovered that, or made that observation, before we knew that electrons existed. Okay? Process that a little bit. Electrons, those little negative things that float around our atoms. Okay? The reason we know we have electrons because of Thomson in the 1890s, which then meant we had protons, which then meant we had a nucleus. Markovnikov made his observation before we knew we had the structure of an atom. That is pretty astonishing that he made this observation, and yes, I grant him credit for that. But I don't grant him credit for making what is now an incredibly obvious observation if we look at the electronics. You know what an electron is. You know what a proton is. Use that knowledge. Okay? What happens with another feature or problem with our pi bonds? Well, it's the pi bond that reacts. The pi bond happens to be located in what orbitals? P orbitals. And p orbitals happen to be both above and below the plane of the atom, which means the electrons can either come out from above or from below. Does that change the directionality of that bond? One goes up, one goes down. Yes, it does. Okay? So we have a stereochemical effect that can possibly rise out of our addition reactions. And we have to be aware of that when we look at our products and we predict our products. That's why when you looked at set 1, there is stereochemistry showing up because you're doing addition reactions. Some addition reactions force particular chemistries. Others do not. So we have to be thinking about our reagents and the complications of them as we move through it. Okay? When we look at our additions, we've got our divisions within our textbook, the Carty textbook, if you're going to use ours. Activate the pi bond by reacting it with an acid. Acids are very, very positive. Remember, we're talking about our Bronsted, so H+. So we're going to make the pi bond react by giving it something incredibly positive. The electrons come out, react with that. We now have a carbocation. How do we stabilize the carbocation? That's chapter 11. Chapter 12, okay, we use another Lewis acid, okay, another positively charged atom, but this time it's not hydrogen. Okay, well, if we have a positively charged atom that's not hydrogen, it's no longer an acid, it's an electrophile. Okay? I don't want to use the Lewis terms or try to back away from them as much as possible. So I now use electrophiles to force the pi bond to react. That's chapter 12. Radicals do whatever the hell they want, unfortunately. I can activate the pi bond by reacting it with a radical. That's chapter 25. Okay? So we are responsible for knowing all of those. Those are all officially first semester. We'll review kind of some new stuff as part of that. Okay? What is the big difference about this structure if we're going to react it with a strong acid? First off, give me a strong acid. HBr. Good choice. Actually, let's see. Yep, good choice. That was totally unintentional, but just wasn't working. So HBr. Okay, the most reactive thing present now. And so this is something I'll constantly ask. What is most reactive? So well, there's a pi bond, so I need to do an addition. Maybe. Maybe the pi bond's not going to react. Find the most reactive thing. The most reactive thing here, that's the other thing that I throw into this, which can be a bit dicey sometimes. Okay? I like to do what I call the face test. I throw an alkene into my face. I don't know. It might hurt. I throw hydrobromic acid into my face. That hurts. Stop that. That's the one I want to focus on first. Why is that one dangerous? H+. I now have my first reactive species. I need to neutralize that H+. What do I need to find in the other reagent?
Electrons.
Electrons. Where are there electrons in the other reagent? The pi bonds. Now the pi bonds can react. Is there a difference between those pi bonds? No. There isn't. I picked that structure for that very reason. So when we look at our structures, it's not just saying one negative, one positive. We now have two negatives. There's two pi bonds that could react. We have to evaluate which one is more likely to react. Since they're both the same, it doesn't matter. So I can react. In this case, I'm reacting the leftmost one to generate our product. So there's our HBr. Whoop, come on, arrow. Doop, doop. That puts the positive charge at the secondary position, not the primary position. You'll notice I've also drawn a bottom one. Well, that's because the other pi bond reacted, right? What was the difference between the pi bonds? Nothing, which means regardless of which pi bond do I react, what should I get? Rhymes with fame. Good enough. Same thing. I get the same thing. So where's that second structure coming from? I'm calling you on the spot, Amber, because we had this conversation. Look at what's given. How do you know that's where that second structure came from?
Resonance.
There you go. You have the same mistake.
We can use the information given to us. We have the double-headed arrow pointing from one to the other. What does that double-headed arrow mean? Resonance. What happened? Those pi electrons shifted over to generate the bottom structure. That means there's two positively charged species, which means there's two positively charged species that I need to be concerned about continuing on in the rest of the reaction. Okay? As soon as I form the first one, I have to decide that's bad, stabilize it. I can stabilize it by going outside. I can also stabilize it by looking inside. Inside gives me resonance, outside gives me a final product. Just because I want to finish the question faster doesn't mean I should draw just the product. I have to evaluate that resonance and see if it generates a new product. When do we end up finding? Well, you get two different products. Two reagents, two different products come out of this. Okay? Since I'm over time, we'll leave it with one kind of cliffhanging question. Which product is the major product? I got two tops. We got one to the bottom. There's 12 people. That's 5. I'm not even saying counting who said what. You could just throw it out there. Because then we're done, right? Just need that. Ooh, 2 more. That's 9. Where are we? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I didn't think there were 12 people. That's 9. 2 people need to guess. I don't even know who those 2 people were. So anybody could guess. Seriously. Thank you. There we go. We're good.